Okay, so we've got this carriage of mass 240 kilograms, okay, and it travels from A to B, okay, and we've given all this information, and we're told A is 30 meters above the ground, B is 22 meters above the ground. Now, it's up to you where you define your zero potential energy, okay? You might find it easier just to put it on the ground here, okay? Or you could even put it at B if you wanted to, okay? Work it out at B, and there may be a little bit less work to do then if you put the zero potential energy here, okay? But you have to think sort of what works best for you there. To keep it simple, I put zero potential energy here on the ground, okay? And we're told it leaves A with speed 2 meters per second, and we need to work out the speed it is when it gets to B, okay? So we need to sort of think about conservation of energy here, okay, energy principles, but also there's work done, isn't there, being done here, because there's a resistance to motion, okay, as the carriage moves along. So what I'm going to do here, I'm going to first of all consider the energy that it's got at A, okay? So let's look at the energy it's got at the start. So at A, it's got two types of energy, isn't it? It's got kinetic energy and it's got potential energy at A, yeah? So the kinetic energy, okay, is that formula, remember, half mv squared, and then of course potential energy is mgh. So, well, we know the mass is 240, and we know the speed of it is 2, so we've got to square that, okay? And then mgh, well, the mass is 240, gravity is 9.8, and the height of it is 30 at A, right? So maybe I'll work these out individually here. Okay, so that's going to be 480, okay? And then we've got here 70,560. Okay, so if I add them together, I get 71,040 joules, the energy then at A. Okay, so we look at the energy at the start. Now let's think about the energy at the end, energy at B. Now, of course, there's things we don't know here at B. Okay, certainly don't know what the kinetic energy is at B, because we don't know the speed. But we know what the potential energy is at B, don't we? Okay, so kinetic energy at B would be half the mass, 240, and then we'll just put V squared, right? Because that's what we're trying to figure out. Potential energy at B will be the mass, 240, gravity is 9.8, and the height is 22, okay? So this turns out to be 120 V squared, okay? And then I get my calculator on that. I get then 51,744. So that's the energy there at B, okay? All of that, of course, is joules. Now, what we can't say is that the energy at A is equal to the energy at B, okay? Because not the energy here hasn't been conserved, hasn't it? Okay, we've lost energy. However, we can work out how much energy is being lost, okay? Because we're given, aren't we, the resistance force, which is constant, and we're given the distance, okay? And we know how to work out energy lost then by working out work done using that formula, okay? But what I'd like you to think of here, right? I'd like you to think about, and we call it the work energy principle, okay? I want you to think how these two relate to each other, okay? So, applying this work energy principle, I want you to think the energy at B, at the end, yeah? Where we are at the end here, the energy at B is made up of the energy that we started with at A. Of course, it's not equal to, isn't it? Because we've lost energy due to the resistance to motion. So the energy at B is what we started with at A, take away the work done, okay, against resistances. Okay, so we know the energy at B is 120 V squared plus 51744, okay. We know the energy at A is 71040, okay, right? But then it loses energy along the way, doesn't it? Okay, due to the work done against resistances. Now, how do we calculate work done? Well, remember, work done is force times distance. And we were told, let's go back, I can't remember what the number was now. Resistance of magnitude 132 newtons, so that's the force. And the distance, of course, of the track we were told was 88. Okay, so that's the work done against resistance. So just do a bit of equation work here and you'll get to the answer. Okay, so we have here, we'll work that out, 11616. So 120 V squared will be 71040, take away 11616, take that over to the side, 51744. So 120 V squared will be, let's work that out there, 7680. To get V squared then, of course, you divide by 120. So I get, oh, that comes out nicely, 64. So that means then V has got to be 8 meters per second.